Okay, so in the previous video, we talked about buffers and we said that a buffer is a solution that contains an appreciable amount of your weak acid and conjugate base that is capable of resisting changes to pH upon the addition of strong acid or strong base. And we said again that we said this idea that we need both our weak acid and the conjugate base for the reason said right over here. Okay, look. So either if I add strong acid or my strong base, so these are my strong acid and strong base, I'm going to need my weak acid to neutralize the strong base, or I'm going to need my conjugate base in order to neutralize the strong acid being added so that we can form water as a byproduct and the strong acid and strong, or weak acid and conjugate base. So the idea here is that you always need to have an appreciable amount of both your weak acid and conjugate base so that you can resist changes to pH when I add in my strong acid or my strong base. Now, what does it mean to have an appreciable amount? Well, you might think, well, if we want to cover our bases, we probably want to have a 1-to-1 ratio or a 50% 50-50 mix of our weak acid to conjugate base. And so the question is just asking the same thing based on what we just covered. What do you think the optimal ratio of weak acid conjugate base is? And like we just said, you would think that a 1-to-1 ratio is going to cover your bases. So no matter if I add strong acid or strong base, I'll be able to resist changes to my pH. And that's the idea here is that you have a perfect buffer, and we say you have a perfect buffer when you have that 1-to-1 ratio of weak acid conjugate base. Now you might ask yourself, well, how do I know I have that 1-to-1 ratio of weak acid to conjugate base? And the way that you know this is you have to compare the pH versus the pKa in order to know that you have an optimal ratio of weak acid to conjugate base. And anytime you're confused on what your ratio of weak acid to conjugate base is, you should always go to this handy-dandy equation called the Henderson-Hasselbalch equation, okay? And you're going to plug into this equation to find the ratio based on the ratio of weak acid conjugate base based on the pH versus the pKa. So in this case, we said that when the pH equals to the pKa, we have a 1-to-1 ratio of weak acid to conjugate base, and we have that perfect buffer. So let's just prove that to ourselves. So if I plug in over here, pH equals to pKa, and I'm going to now plug in for my weak acid to conjugate base because I know I have a 1-to-1 ratio. I'm going to go 1 over 1. The log 1 over 1 is 1, and the log of 1 over 1 is going to be 0. So notice how my pH equals to my pKa when I have my perfect buffer. So if I gave you a carboxyl group and I told you when will I have a 50-50 mix between the carboxyl group and its conjugate base, okay? So this is another way of saying HA versus A minus again. So when will I have a 50-50 mix or a 1-to-1 mix of these two? The time when I'll have a 50-50 mix is when my pH is equal to my pKa, okay? Which is equal to, in this case, around 2.0 if this was connected to a free amino acid. But the idea here is that you're going to have the perfect buffer when your pH equals to pKa, and you're going to have a 1-to-1 ratio. Again, the whole point of this is to come back over here, and you need both the weak acid and conjugate base so that you can neutralize a strong acid or strong base. Now, we don't live in a perfect world. We're not going to always get a 1-to-1 ratio. So you can have a 1-to-10 or a 10-to-1 ratio of weak acid to conjugate base. And by this, because it's kind of hard to see on this table, I kind of drew out a number line for you guys, okay? So the idea here is that we just said that 1-to-1 ratio is the perfect buffer, and that's where the pH equals to the pKa. But this table is telling you that as long as you're within a 1-to-10 to 10-to-1 ratio of weak acid to conjugate base, so if I go over here and I fill this in, as long as you're 10-to-1 to 1-to-10 ratio, you're still going to have an appreciable amount or an enough amount of weak acid to conjugate base so that it's still considered a good buffer. And now you might ask yourself, well, how do I know I'm at that range where I have a 1-to-10 or 10-to-1 ratio? Again, you can always go back to this Henderson-Hasselbalch equation. And I'm just going to do it for the example of, let's just say that we had the pH being 1 over the pK. So let's say that our pH in this case is going to be equal to 8, and our pK is 7. So I'm doing this example right over here. Okay, so I'm trying to see how I can get this ratio. So I'm going to plug it in over here. Okay, then I'm going to subtract 7 from both sides. That's equal to 1 log of a minus over HA. So now, to get rid of the log, what do? We do 10 to the power of. That gets rid of that, 10 to the power of. So that's 10 to the power of 1 is equal to 10 over 1, which is equal to a minus over HA. And notice how we got that 1 over 10 ratio. So the 1 corresponds to the HA. The 10 corresponds to the A minus. And we got that 1 to 10 ratio of HA to 10, A minus. We got 1 to 10 HA to A minus. And we're saying that that is the edge of our good buffering region right over here. So if I plugged it in over here, so this is pH equal to my pKa plus 1. And now I could do the same thing if I wanted to do pH equals to pKa minus 1. I'm not going to go through the calculations for that, but just so that you guys can see what's going to happen, if I plug in 6 over here, I can subtract 7 from both sides, and I'm going to get a negative 1. And then notice how 10 to the power of minus 1 is 1 over 10. So I get the other ratio. Okay, so I'm going to plug in over here, pH equals to pKa minus 1. So as long as you're between a 10 to 1 to 1 to 10 ratio, so meaning that 9 to 1, 8 to 1, 7 to 1, all the way to the other side of 1 to 2, 1 to 3, 1 to 4, all the way to 1 to 10, you're going to have a good buffer. As soon as you get 1 to 11 or 1 to 12, anything over that 1 to 10 ratio, you're outside of your good buffering region, and you are no longer going to have a good buffer. So for example, if I told you that my pH is 8 and my pK is 6, that means that I no longer have a good ratio or an appreciable amount of weak acid conjugate base because I'm 2 units above my pH. Okay, so the idea here is that you always want to be plus or minus 1 of your pKa. So just to give an example here of what I'm trying to say, so I'm going to just draw out a generic amino acid. We're going to go like this. We're going to put alpha carbon, H, and the alpha amino group right over here. And we're going to say that this is a free amino acid, so the pK of the carboxyl group is 2.0. This is 9.5. And we're going to say, can this amino acid buffer at pH equal to 6? Well, let's find out. So I have 2 pKs that I drew out over here. I have 9.5 for the alpha amino group, 2.0 for the alpha carboxyl group. And we just said that the perfect buffer is where my pH equals to my pKa, but I can have a good buffer as long as I'm plus or minus 1 of that pKa value. So if I go over here, I'm going to just take my pKa values. Here's 2.0, here's 9.5. So my buffering range for the carboxyl group is going to be 1 to 3, because that's plus or minus 1 of that pKa. Now for my alpha amino group, plus or minus 1 of that is going to be 8.5 to 10.5. So at pH 6, this amino acid is not going to be a good buffer, okay? So it's not going to be a good buffer. We're going to say it's not a good buffer. Now, this doesn't mean that it's not a good buffer in any situation. If I instead asked you for, can it buffer at pH of 9.5, then you're going to say, yes, it can. But because we're asking specifically at pH 6, we're going to say that this is not a good buffer at that specific pH. If the idea of pKas versus pHs confuses you, I'm going to make another video on pH versus pK, but hopefully this helped on this idea.